All right, it's 8:30. Let's go get started. Good morning, everyone. How's everyone doing today? All right. Oh, sorry, was one said something on Zoom? Oh, maybe not. Anyway, talk to myself. All right, so today the plan is we're going to continue with our lectures for Laplace transforms. So on Monday, excuse me, on Tuesday, we introduced the idea of Laplace transforms, and today we're going to continue on with that. Well, I'm hoping what we get to today is we actually get to start solving some differential equations with Laplace, but we'll see. That's a little bit ambitious. All right, so one announcement I want to make is that there's yet another typo in the homework solution, so I apologize for the confusion, but there's a typo in the solution for problem 2E. So problem 2E, there's a lot of terms in the results, but one of the terms has a typo, so it's the constant term. And so I believe in the solution, it's a minus 76/27, but the correct answer actually is a plus 52/27. Okay, so if you're working on problem 2E and you're not getting a matching term for that answer, that's the reason is because I made a mistake in my work. So I apologize for that. Hopefully, it didn't cause too much confusion. I haven't had a chance to update the homework PDF yet, just because yesterday I was really busy with stuff. But I plan on doing that today after class. Okay. But I wanted to tell everyone in the lecture today, just so that you know. All right, so I think that's all my announcements. Remember, homework 2 is due tomorrow. So homework 2 is due tomorrow Friday at 11:59. Make sure you're done. So I know. So problem 2 is by far the longest problem on the homework. Once you're done with problem 2, then 3 and 4 are ordered by comparison. Okay, so.
Am I able to return in my homework?
Yeah. So if you're turning it on Canvas, it only really shows me the most recent submission. And so if you want to resubmit, if you notice a mistake in your work, you want to resubmit before the deadline, you can go ahead and do that. It does show me that you submitted earlier, but it only shows me the latest one. All right. Any other questions I can answer before we get started today? Okay. All right, so let's go ahead and pick up where we left off. And where we left off on Tuesday was we were talking about computing the inverse of Laplace transform. Okay. So just to kind of recap a little bit from Tuesday, we're introducing this new idea of a Laplace transform, because kind of the argument that I'm making to you is that it's kind of a different way to solve differential equations. We haven't really gotten to that point yet. We're kind of still in the very beginning stages of just introducing what this Laplace transform is. And then today we'll learn more about it, and then hopefully we'll get to the point where we can solve differential equations. But the general idea with Laplace transform is that we can take our differential equation, which has a bunch of derivatives in it, and through the Laplace transform, we can transform that differential equation into an algebra. Because what we saw from the first 3 weeks is that solving differential equations, it can be quite tedious, especially once you have a bunch of kind of added stuff to it. And so when you have initial conditions, when you have non-homogeneous terms, there's quite a lot of steps that you have to follow in the solution. And so what we'll see, hopefully today we'll see this, that when you apply the Laplace transforms, it kind of solves everything at once. And so there's some people might argue it's less to go through. Okay? But depending on how you like partial fraction decomposition, you may feel differently about Laplace transforms. And so what we introduced on Tuesday was just how to take the Laplace transforms of a function and switch from the physical domain to the Laplace domain. So that's all we've done so far. So remember, the Laplace domain, the variable that we're using is s. Okay, so we're basically transforming a function. Usually it's a function of t. So it's a function of t into a function of s. Okay. And we went over kind of the integral, how to perform the transform via the integral. But at the end of class on Tuesday, what I mentioned was kind of the more common way to take the Laplace transform is to just kind of look it up in a table. Okay. And so let me go ahead and show you the table again. So again, this table was in the notes, and so this is on page 5 of the notes. And so, when you're doing homework 3, you can just use this table. Okay. I don't believe I'm asking you a problem to actually use the integral transform. But again, the reason I introduce the integral transform to you is so that you know where this comes from. Because otherwise, if you just look at this table, this all just kind of seems like magic. Without any kind of knowledge of where these things came from, right? So I showed you the integral form on Tuesday, just so that the value in this table, they do come from something. There is some logic behind it. It's just that transform is usually a little bit too tedious to do on a regular. Okay. All right, and so what I wanted to do, the first thing I wanted to do today, is to give you a few more examples of how to compute the inverse transform. Okay. And so we did a lot of examples last time on how to do the forward transform, so how to take a function of t and transform it into the Laplace domain. Today I wanted to show you a couple more examples of if you have a function of s, and so Laplace domain function, how you transform that back to the physical domain. Okay, and so we're going to use this table. So you don't have to commit it to memory, but just know that it exists. And I'm going to reference this table in the next few. Back to iPad. Okay. So let's start with a fairly simple one. All right, so let's say that we have a function of s, so Laplace domain function equal to 5s divided by s squared plus. And what we want to do is we want to compute the corresponding physical domain function. In this case, it's little f of t. So we have a function of s, and we want to compute a function of t. And so, in other words, this is an inverse Laplace problem. Okay. All right. And so, the whole game that you have to play with the inverse Laplace is that you have to basically look at this function and try to fit it to one of the entries in the table. And the way that we do that is we use some algebraic manipulations. This one's fairly simple, but then the one that we're going to do after this is going to showcase a little bit more complex stuff. All right, and just like I mentioned on Tuesday, when I do these examples, I'll say, oh, it may seem obvious that this looks like cosine, or this looks like sine, or this looks like an exponential function. right? When you're first doing these, it's super not obvious. And so, don't try to look at these and it's like, oh, I didn't get that at first. And so I must be really bad. So I'm only good at this because I would have been doing this for like 10 years. And so I can look at these and tell you exactly what the inverse Laplace is. But when you're first doing these, it's almost like a puzzle almost. So it's not going to be immediately apparent. So, just for this section, I want to give you a lot of examples just so that you can see a lot of these stuff. But even beyond that, it's going to take some time for you to kind of build the intuition and kind of build kind of that pattern recognition between what you see and how you fit that into the table. Okay, so don't rush these. That's what I'm. Okay, so for this particular problem, one thing I noticed kind of right away is that there is a constant out here in front. Okay, so what I'm going to do is I'm going to kind of separate that from the other parts. Just to make it a little bit more obvious. Okay, so let's pull the 5 out. And so if we pull the 5 out, then we have in the parentheses, we have s over s squared plus 9. Okay. I'm going to do one more thing just to make it a little bit more obvious. And so I'm going to take that 9 and I'm going to replace it with 3 squared. Right? So 9 is just the same thing as 3 times 3. Right? 5 times s over s squared plus 3 squared. Okay. So let's look at this expression here that I've kind of worked out. Okay. And so we have s up top. And so having s up top is kind of an indicator. So having an s up top, that tells us that this is probably going to be a cosine function. Okay. Okay, when you have s up top and s squared on the bottom, that's a pretty telltale sign that this is cosine. Okay. And this 3 right here, this 3 is playing the role of omega. Okay. And so if we look at the table, and you look at the Laplace transform, cosine omega t, this is equal to s over s squared plus omega squared. Okay. So this right here is from the table. And so what we've gotten from this is something that looks very similar. So we have s over s squared plus 3 squared, where if we say 3 is the same thing as omega, our frequency, then this is okay. And so let's use the table to take the inverse Laplace of this. Okay. And so f of t in this case is equal to the 5 just comes right down, and so the 5 is just a constant. And so remember the constant we can just kind of pull right out. Because Laplace transforms are linear. And this multiplied by cosine of 3t. And that is our solution there. So taking the inverse Laplace of 5s over s squared plus 9 gives us 5 times cosine of 3t. We did that very quickly. Due to the table. All right, any questions on this example here? All right, so that's kind of the game that you're going to play. 32 years old, my voice is still correct. So that's kind of the game that we're going to play, right? And so we have our functions of s, and we're just going to try to manipulate it until it looks like a table guide. Okay. Let's do one that's a little bit more complex. So we have f of s with f of s is equal to 1 over 3 minus 4f plus 3 minus 2f all over s squared plus 14. All right, and so just like the last problem, what we're interested in here is we want to take the inverse Laplace of this function to get little f of t. Okay. And so of course, this one's a bit more complicated. And so, we're gonna have to do a little bit of work here. But with a little bit of algebraic manipulations, what you'll see is that this can also fit into some table values. But we're gonna use multiple table values. Okay. All right, so just because it's kind of similar to the previous example, let's work on the second term first, okay? Because what we have there is s squared, in the bottom, we have s squared plus 49, okay? And if you are familiar with your perfect squares table, you know that 49 is just the same as 7 squared, okay? And so we're in kind of good shape there. So, basically what we're gonna do is we're gonna try to manipulate that in order to look like that. And so what the first thing I'm going to do is that I notice that I have two terms in the numerator. And so what I'm going to do is I'm going to split that into two fractions. Because we have an operation there in the numerator, we know that we can just kind of split those into two separate functions, add them together, or yes, in this case, we subtract them with the same denominator. And so this splits into 3 over s squared plus 7 squared minus 2s over s squared plus 7 squared. Okay. Right. So already we're in business, and so if we look at the second term there, the 2s over s squared plus 7 squared, this looks very similar to the last example, right? So if I isolate this right here, this looks very, very similar to the last one, except instead of 3, we have 7, right? And so we know the inverse Laplace of this will be cosine of 17. Okay. Well, that's good. And so, we're gonna, or I guess, if we want to include the 2 there, put the 2 up there too. Okay. And so that term is done. And so, we've taken the inverse Laplace of that. Let's just kind of work on everything else. Okay. Let's tackle this term next. All right, so we have a 3 over s squared plus 7 squared. And so, obviously this is not going to be a cosine because we don't have an s up top, right? So in order to do cosine, we need to have an s in the numerator. And so if you look at the table, the one this is most similar to is actually going to be sine. We have the Laplace transform of sine omega t omega over s squared plus omega squared. Okay, so this fits this function pretty well because the Laplace transform of sine, we don't have an s up top, but we do have omega, and so omega here is just a constant, and so this is probably what most closely resembles this function here. Okay. The problem with this is that we're not quite there because if you look at the structure of this Laplace transform. The constant that's on top of the numerator has to match the frequency of the sine function, right? And so these two have to match. These two have to match in order for us to actually perform that transform. Right now we don't have that because in the denominator we know that we have a frequency of 7, and so we know omega here is equal to 7 for this function. Okay. But we don't have 7 up top. And so what we have up top is 3. And so we need to basically change this into a s. Because once we change that to a 7, then we can directly apply this inverse Laplace. Okay. Let me do this. So let me take our function here. And let me do this. And so let me multiply it by 7 over 7. Okay. And so if we do that, if we take the 3 out in front, so we have 3 by 7 over s squared plus 7 squared. Okay. I basically introduced a new 7 and I've taken out the 3. And so inside the parentheses now, we have exactly what we need to take the inverse of. But right now, this is not algebraically correct. We can't just take a 7 and just pull it out of our ass, right? We need to actually, make sure it's still consistent with the original equation. Okay? And so to do that, I'm going to divide a 7 on the outside. Okay? And so a lot of Laplace transforms are kind of like this. And so you kind of have to pull, you have to do kind of some constant manipulation or algebraic manipulations. And sometimes it involves something like this. Okay? So basically what we did is we just factored out 3 and we multiplied it by 7 over 7. 7 over 7 is just 1. So we can always multiply by 1. That's no problem. But the reason we do that is so we can put 7 inside the parentheses and pull the other 7 outside the parentheses in the denominator. Because now what we can do is what we can say is that this quantity in parentheses, when we take the inverse Laplace of this, we get sine of 7t. Okay. And then the constant just kind of comes along for the right. So the inverse Laplace of this entire term right here is 3 over 7 sine of 7t. All right, any questions on that? Okay. All right, so we're 2/3 done, and so we did the second term now. So the 3 minus 2s over s squared plus 49, that one is taken care of. Okay. But we still need to take the inverse Laplace of this. All right. And so, just like before, we're going to look at our table. And what we notice here is that in the denominator, we have kind of a first order polynomial in s. Okay, so it's just a linear function. And so what this tells us that it should look like the Laplace transform of an exponential. So from the table, what we have is the Laplace transform of e to the at is equal to 1 over s minus a. Right, so this is what this one kind of looks like. It's not quite there yet. We need to manipulate it a bit, but this is kind of our goal. Okay. And so let's try to manipulate this first term until it gets into that form. All right, so first thing I'm going to do is I'm going to factor out a negative. And so I factor out a negative. We have a minus out in front. So we have 1 divided by 4s minus 3. Okay. So that gets us closer, right? Because in the table, s term comes first, and so we need to factor out that minus sign in order to make that happen. And so the other issue that we have here is that we have a 4 out in front. Okay, and so we need to get rid of that 4 in order for this to. And so to get rid of that 4, all we have to do is factor out a 4 from the denominator. Okay? And so if we do that, we get a minus 1 over 4 multiplied by 1 over s minus 3. Once we've done that, we've gotten this into the form that we need to, because this is s minus a constant, right? And so the constant here is just 3/4. And so now this is ready to inverse Laplace. So when we inverse Laplace this, we get e to the 3/4 t. Okay. And then the constant in front, that just kind of comes along for the right. And so we have minus 1. So now that we've taken the inverse Laplace of all 3 terms, we can put it all together. And so we have f of t in total is equal to minus 1/4 the 3/4 t plus 3 over 7 9 7t minus 2 cosine 7. And so that is the result of this problem. Any questions on this? Yeah.
For the 1/3 by this, you just multiplied it by -1 to make it look more similar to the.
Exactly. Yeah, because our original function here was 1/3 minus 4s. And so I multiply by -1 so that I get, the s in front, because we need s minus something in order for it to go back to the table.
And then would the inverse Laplace still look the same even if you didn't multiply it by -1?
You need to multiply by -1 because the s needs to be positive in the denominator. Yeah, so if you don't multiply by the -1, it's not going to look quite the same as the table. Any other questions on this example here? Okay. All right, so there's a couple examples with the inverse Laplace, right? And so, like I said, these take practice. And so when I'm doing it in the class, I'm doing them fairly quickly because I've almost committed that table to memory because I've done this for so long, but not quite. And so, I can see these patterns really easily, but, like I said, the first time you're doing these, kind of take your time, it may take some trial and error in terms of, how do you get these to look like the table. It's going to take some trial and error to even determine, what table value are you even aiming for. And so, I know it's easy to get frustrated with these, but, don't be afraid to ask for help. I'm always here to help you. And, I think by seeing a lot more of these, by doing more practice, you kind of get better. Okay, so just kind of have some patience with this. Okay. So let's move on to a new topic. And so I want to talk about the first, what's called the first shifting theorem of Laplace. Okay. And so the first shifting theorem, basically this kind of highlights a very nice property of Laplace that we're going to make use of a lot. Okay? And so the idea with the first shifting theorem is that if you multiply your physical domain function by an exponential, what that does is that it ends up shifting your Laplace domain by a certain amount. Okay. And so this is the first shifting theorem. And so the fact that it's the first one, it implies there's a second one. But we're not going to cover the second one, probably not until the end of it. Okay, so the first shifting theorem is like this. And so basically, if you know, and so this is known. And so if you know the Laplace transform of some function, f of t, and you know its Laplace transform, f of s, okay? And so let's say that, let's just say, for instance, this, you look it up in a table, okay? Then, if you take that function f of t and you multiply by an exponential, okay? And so you multiply by e to the at f of t, okay? And you take the Laplace transform of that. So you take the Laplace transform of the product of an exponential function multiplied by your original function f of t. Okay. You don't actually have to go through the table or to do this, or you don't have to go through the integral. What you can say is that just by multiplying that function e to the at, what you get is f of s minus a. Okay. And so in other words, if you have a function and you multiply it by e to the at in the physical domain, what that will do is that it's going to cause a shift of a in the Laplace domain. So this is nice because this is going to show up quite a bit in our differential equations. And so we're going to have situations where, and we're going to go both ways. And so we're going to have a Laplace situation where the S is going to be shifted by A. Okay. And then we want to take the inverse of that. We know that we just multiply by e to the at. Okay. Let me just do a very quick example. This is going to show you what this means. Okay. And so from the table, we know that the Laplace transform of t squared is equal to 2 over s cubed. Okay. Right, that's just the Laplace transform of t squared. And so if we do, let's say we multiply t squared by e to the 7t. Okay. We want to take the Laplace transform of this. Okay. Normally, you would look at something like this and you would say, like, "Oh man, like I need to take the integral expression for this because this isn't in the table, right? There's no expression in the table for an exponential multiplied by t squared." The reason for that is that you don't need to do the table. So what you can do is you can take the Laplace transform of t squared. Okay. And then everywhere that you see s, you're going to replace it by s minus 7. Okay. That's all the shifting theorem is. So if you multiply by an exponential function, you just replace s by the shifted s. Okay. And so for this case, our Laplace transform for t squared is 2 over s cubed. Okay. And so if we multiply by e to the 7t, then we're going to replace s instead of s cubed. We're going to have s minus 7 cubed. Okay. Any questions on first shifting theorem here? Okay, let's do one more example with the first shifting theorem. And this one is going to be a common case when we start doing our differential equations. So this is going to be an example with a damped oscillator. And so a damped oscillator is basically one where you have an oscillating function, sine or cosine, but then there's a decaying exponential after function. And so let's say that our Laplace transform function f of s is equal to 3s minus 137 all divided by squared plus 2s plus 0.1. Okay. So let's work on this example here. All right, so let's start with the denominator. And so let's look at that. And so we have a quadratic function, right? So we have s squared plus 2s plus 401. Okay. We don't quite have anything like that in the table, right? And so we don't really have a quadratic function of that form in the table. But what we can do is we can work on this in order to get it to look like something in the table. Okay. Keeping in mind that we now have our first shifting theorem in our arsenal. Okay. And so I'm going to do something on the bottom that you may not have seen in a very long time. Okay. I remember when I first learned this, I was like, man, I never thought I'd do this outside of high school. Okay. And so what I'm going to do on the bottom there is I'm going to complete that width. And if you forgot how to do this, don't worry. I remember when I first learned this, I was like, I do not remember how to do that at all. Okay. Okay, so to complete the square, basically what you're going to do is you're going to look at the first two terms of the quadratic, right? And so we have s squared plus 2s. Okay. And what we want to complete the square, we basically need to add this by to something. Okay, we need to add a constant here in order to get it into this form. So we basically want to complete this this form. And so we want to turn it into basically a squared, quantity squared. Okay. And so the first thing you're going to look at is you're going to look at which term is in the linear sum. Okay, so we have 2s there. And so the square that we're looking for, and so we call this 2. And so let me give a generic name for that 2. So instead of 2, let me call this, call it big A. Fine. And so the square that we're looking to complete is going to be s plus a over 2 squared. Right? Because when we take a square of a of that s plus a over 2, what we end up with is s squared plus a over 2 plus a over 2 plus s a over 2. Okay. And so in order to complete that square, the whatever the linear term is there, that's going to be divided by 2. And that's going to be our completed square. And so what that means that the constant that we are going to multiply by, we're going to add to, is a over 2 squared. Okay. And so for this problem, we have 2 over 2 squared. And so 2 over 2, of course, is 1. And so 1 squared is 1. Okay. And so to complete the square, we just need to add 1 to this. So we have s squared plus 2s. Okay. That's one part. And then what we're going to do is we're going to basically borrow 1 from what's left there. Okay. So we have plus 401 there. And so if we take 1 away from that, then all we're left with is plus 4. Okay. And so what that does is that now we have s plus 1 squared plus 400, and this is our new denominator. Okay, let's go ahead and write this down. So we have f of s is equal to bs minus 137 divided by s plus 1 squared plus 4. Any questions on this? Brush off your high school math. You have to complete the squares, and so I know it's been a while for some people. So the thing with Laplace that we're going to be doing a lot of I call them algebra tricks in order to get them these to work out. Okay, so some of these tricks you may not have used in a long time, but when you're you said you're going to use this one day. Well, this is that one day, right? So this is the day that we're using a lot of these old tricks. Okay. All right, but we're not quite done yet, right? And so, all we've done is just complete the square on the bottom. But remember, for this problem, we wanted to take the inverse of Laplace. Okay. Well, let me highlight something for you. And so we did all this work to complete the square on the bottom. And so, what exactly does that give us? And so if we look at the bottom here, this almost looks like an S, but shifted, right? So if we just imagine that as just s squared plus 400, that's something that's a little bit more familiar to us in terms of looking it up in the table. Okay? We don't have an s squared plus 400, but we have an s plus 1 squared plus 400. Okay? And so that quantity s plus 1 squared makes us think that this is probably a shifted s. Okay, and the shifted amount is -1 in this case. Right? And so this is looking like a problem where we're going to have to utilize the first shifting theorem. Okay. And so let's use that to our advantage. And so I'm going to do the same thing as I did in the last problem. And so I'm going to split these into two terms. Switch the column back. This is obnoxious. All right. And so the first term is going to be 3s divided by s plus 1 squared plus 400 minus 137 over s plus 1 squared plus 400. Let me replace the 400 just to make it a little bit more clear. And so the 400, another way to represent that is 20 squared. Okay. So we know from this problem, this looks very similar, or we're kind of gearing towards sine and cosine, right? And so remember, sine and cosine, kind of the most distinguishing characteristic of their Laplace transform is that in the denominator they have s squared plus omega squared. Okay. We kind of have that already, so we have the s squared, and we know that our omega in this case is going to be 20. And so it kind of looks like we're gearing up to transform this back into sine and cosine. Okay. So let's do them kind of individually. Okay. So let's do this first term. So we have an s up top, and then s squared plus omega squared on the bottom. And so this looks like cosine. Okay. But we're not quite ready yet to transform this back into cosine. Okay. The reason for that is that we have this shift, right? Okay. And the way the shift works is that you have to replace every instance of s with s plus 1. Okay. That means that this s up top has to also be s plus 1 in order for us to do the inverse. And so we have a little bit more algebra to do to kind of turn this into cosine. So let's go ahead and do that. And so up top, let me take the 3 out. And so we transform that into f plus 1. We have f plus 1 up top, s plus 1 squared plus 20 squared on the bottom. Okay. So now what's in the parentheses there is ready for us to invert. But just like before, we can't pull that s plus 1 out of our s, right? We need to kind of account for it later in the problem. And so what we did basically here was we added a plus 1 times 3 over s plus 1 squared plus 20 squared. Okay. And so to account for that, we need to subtract 3 for s plus 1 squared plus 20 squared. Okay. So this term right here accounts for okay. And so this term kind of balances out the fact that we did s plus 1 up top here. Okay. So we basically added plus 1 and we subtracted that plus 1 times 3. Okay. And then what we also have still is we still have this minus 137 over s plus 1 squared plus 20 squared. Yeah. Let me go ahead and combine these two. And so if we combine those two there, we get 3 times s plus 1 over s plus 1 squared plus 1 squared. Okay. So that first part right there is ready to be inverted. Okay. And so that's going to be a shifted cosine. Okay. And then over here, what we have is 1 minus 140 over s plus 1 squared plus 20 squared. Okay. And so the first term is going to be a shifted cosine because we have an s up top. This one right here is going to be a shifted sine. The nice thing about sine is that s only appears once in the Laplace transform of sine, and so it only appears in the denominator. And so we don't need to do any additional kind of shifting here because the s is already accounted for. Okay? What we do need to account for is the fact that we need omega up top here. And so the frequency in this case is 20, as denoted by the denominator. And so we need to manipulate the top here in order to make it 20. Okay. So let me do this. So we're going to subtract. Let me factor out a 7. And so if we factor out a 7, we have 20 over s plus 1 squared plus 20 squared. All right. We did lots of algebra, a little bit of completing squares, right? So now we're ready to finally take the inverse of this. So both terms are kind of prepped and primed and ready to go. And so we take the inverse, get f of t is equal to, let's bring down our constant. Okay, so the 3 is just going to be along for the ride. And then we have cosine. Okay. But since we had that shift, that s plus 1 shift, that means we have to multiply it by our exponential function. Okay? We have e to the minus t. And with this e to the minus t, this results from the shift. And then we're going to do the same thing for the sine. And so for the sine, we have minus 7 e to the minus t sine. And that right there is our inverse Laplace. Any questions on this example here of the first shifting theorem? Yeah.
You go over when we accounted for the plus 1 again?
Sure. Definitely. Okay. And so, when we accounted for the plus 1 in the cosine term, basically what we need to do is we need to transform that 3s up top to a s plus 1. Right? So the first thing I did was I took the 3 and I just kind of factored it out. Okay? So the 3 kind of just came out just like that. And then I knew that I can't just have an s up there, so I need to have s plus 1. Right? And so by making s plus 1, what I did was I created kind of an excess of that. And so if you if we kind of combine these two steps right here, so let's just look at this term right here. And so we have 3s, and they all are on the same denominator. So I'm just going to kind of put them all into one term, plus 3, minus 3, all over s plus 1 squared plus 2 squared. And so I essentially just added 0 to the function, which is, you can do that. Adding 0 is okay. But I kind of split that 0 into a plus 3 and a minus 3 just so that we can have that s plus 1. Yeah, it's weird. And so, I think probably, in most cases, you're not, you don't usually do math like this. You don't kind of make up terms out of nowhere just for the sake of it. But, when you're doing Laplace, a lot of it is, how do I fit this into the table? And you're gonna have to do kind of weird tricks like this. it is weird. I think, this may be the first time you're kind of doing things like this, but, and again, these things kind of just take a bit of practice. All right, any other questions on this example here? Okay. All right, so let's go ahead and move on. So that's the first shifting theorem, and so we're going to use that a lot, especially in our differential equations. Now let's actually start getting towards that. So let's talk about the Laplace transform of a derivative. Right. So ultimately, what we want to do, just like we've been talking about the last two lectures, is we want to use Laplace transform to solve differential equations. Okay. And so the way that we do that is we take our differential equation and we just take the Laplace transform of that entire equation. Okay? And so in order to make this work, we need to know how to take Laplace transforms of derivatives. Okay. All right. So I have two formulas for you. The first we have the Laplace transform of the first derivative. Okay. Okay, so this will be the Laplace transform of f prime. Okay. You can also, this might be the same as the Laplace transform of df of t. Okay. They both kind of represent the same thing. And so the Laplace transform of the derivative, the way you do this, you take s, you multiply it by big F of s, where big F of s is the Laplace transform of little f, okay? And then you subtract the initial condition, okay? You label these, so f of s is equal to Laplace transform of f of t. Okay. And this little f of 0, this is the initial condition. Of f of t. Okay. Or remember, little f of t is the function in the physical domain. Okay. All right, and so since we're also going to be dealing with second order differential equations, we also need the Laplace transform of the double derivative. Okay. See this as d squared f d squared. And this is equal to f squared, big F, s, f minus s times f of 0 minus f prime. Okay. So remember I mentioned before that, when you're doing Laplace, it kind of solves it all in one. So you don't really have to solve different problems. So you can kind of see one aspect of this here, right? So normally when you solve a differential equation, kind of the traditional way, you kind of solve the general solution first, and then you apply the initial conditions after that. Okay. For Laplace, you don't have to do that because the initial conditions are baked directly into this Laplace transform. Okay. So this is nice. And so, if you have a problem when it's given initial conditions, you don't have to do kind of a separate problem to account for them. You just take by taking the Laplace transform, they're factored in immediately. And so, you don't have to do any kind of worrying. You basically plug them in at the beginning, and then you just kind of don't worry about them after that because you're still all solving the same problem. Okay. All right, so let's see how this works when you're applying them for differential equations. Okay. So let's start with the generic differential equation, and I'll kind of walk you through kind of the three-step process that you need to solve it. Okay. All right, so for our typical differential equation, we have y double prime plus ay prime by, and this is equal to r of t. We're going completely general here, and so we have a non-homogeneous equation. We have a forcing term on the right-hand side. Let's say that we're given initial conditions. So we'll say y0 equal to k0, y prime of 0 is equal to k1. Okay. So this is a second order differential equation that you would normally be given, let's say like in homework 2, okay? But now we want to solve this with Laplace. Okay. And so to solve these kinds of differential equations with Laplace, it's a three-step process. So step 1. Step 1 is to take the Laplace transform of the entire differential equation. And so we have y double prime plus ay prime plus by. We want to take the Laplace transform of this entire thing. And so remember, the Laplace transform is a linear operator. And so when you're applying it to a sum or different terms in expression like this, that means you can just simply take the Laplace transform of each individual term. This is Laplace transform of y double prime plus. Okay. Remember, a is a constant here, so I'm just going to pull it out in front. And so a times the Laplace transform of y prime plus b times the Laplace transform of y is equal to Laplace transform of t. We're taking advantage of that linearity property of, or that linear property of Laplace transforms. Okay. So now that we've applied the linear operator, we can take the Laplace transform of each individual term. Okay, keeping in mind, that we're going to leave some terms generic right now because we haven't solved for them, but we will eventually solve them. All right, so let's do a Laplace transform of y double prime first. So let's go ahead and plug in our formula up here. Okay, and so Laplace transform of y double prime is going to be s squared. I'm going to use big Y of s. Okay. Minus s y of 0 y prime 0. So that's the Laplace transform of y double prime plus a times the Laplace transform of y prime. And so the Laplace transform of y prime is s big Y of s minus y of 0. Plus b, then we have just the Laplace transform of y by itself, and so we're just going to leave a variable for that, and so that's going to be big Y of s. Okay. And then finally on the right, we have the Laplace transform of r of t, We're just doing this generically for now, but generally you'll know what RT is. It's going to be some forcing function. But for now, I'm just going to leave it generic. We'll call big R S. Okay. But remember, this is usually no. We just don't know it right now, just because we're doing it generic. Okay. Let me go ahead and plug in the initial conditions. Y of 0, what do we call Y of 0? We call Y of 0 K0. Okay, so we have S squared Y of S minus S times K0 minus Y prime of 0, K1, plus A times S Y of S minus Y0 K0 plus B S equal to S. For a usual problem, you'll have the initial conditions, and so you won't have them in terms of variables. And so this will be a little bit easier. And A and B, of course, will be numbers as well. But this is just kind of just the generic example, just to kind of show you the process. All right. So that's step one. So step one is basically just take your original differential equation and take the Laplace transform of the entire thing. So now we have everything in terms of S. So there's no more T. Okay? And more importantly, there's no more derivative, right? So everything here is just algebraic expression. We come to step two. So step two, what we're going to do is we're going to solve the algebraic expression for big Y of S. Okay. And so what I'm going to do is I'm going to collect like terms. And so everything with Y of S, I'm going to keep on the same side. We have Y of S multiplied by S squared plus AS plus B. And then everything that's not Y of S, I'm going to move to the other side of the equation. Everything that's not Y of S, I'm going to move to the other side. So that means all the initial conditions, okay, I'm going to move to the other side. And so we have K0 times S plus A plus K1 plus big R. All right, so we've successfully isolated Y of S. The only thing we need to do is we need to divide by its coefficient. We divide both sides by this. We get Y of S equal to, and I'm going to keep each term separate because traditionally you actually kind of solve each term separate. Do K0 A I S squared plus AS plus B plus K1 I S squared plus AS plus B plus big R S S squared plus AS. So this is kind of another instance of this too. So I'm usually not too big a fan of this because I think what this kind of encourages is just to kind of plug into this equation here when you have a Laplace transform. So I don't want you guys to just plug into this formula here. I really want you guys to kind of follow this process, right? So I want you to take the Laplace transform and then algebraically solve for y values, okay? And so, a lot of the situations that we're going to do, it is going to fall into this format. But, what's kind of more important here is that you office more so than just kind of plugging into this equation. Okay, so I do want to see that in your work. So, when you're doing these Laplace problems, I want to see the work of, take the Laplace transform, do the algebra, solve for y of s, and then, go from. Okay. Okay. So usually there's a step 2.5. We'll cover that in a second, but generally once you solve for y of s, there's a step 3. And so step 3 is that now that you have this kind of Laplace expression for y of s, then all you have to do is take the inverse Laplace, solve for y of t. And so, there's not much we can do here because a lot of it depends on the exact form of y of s, but, we did a lot of practice today taking inverse Laplace. Okay, so you kind of follow that process. And and a lot of times you're gonna have to use kind of every trick in the book. So you're gonna have to use, algebraic manipulations. You're gonna have to use the first shifting theorem. Okay. And so there's a lot that you have to do. Completing the square, right? So step 3 is a lot, but usually there's something you have to do before step 3, which is partial fraction decomposition. Okay. Because a lot of times, when you go through this process and you solve for y of s, excuse me, that y of s is not in a form where you can kind of directly invert it. Okay? And so you need to kind of break up some of the denominators. Okay? And so I'll say step 2.5. Not in the textbook, although they heavily tell you that you do have to do this. Okay. Partial fraction decomposition. Partial fraction decomposition to break up some of the denominators. Particularly for this term, okay? And so when you have a non-homogeneous function and you take its Laplace transform, it's going to give you usually something in the denominator. And when you multiply by that quadratic function, you usually get something that you can't invert just straight. Okay? And so you're going to need to decompose it into different fractions in order to do it. Okay? So the reason I list out that step 2.5 is that most of the time that's for most of these problems, that's probably where you're going to spend most of your time. So most of the effort in doing Laplace problems is doing that partial fraction. And we're going to review it. And so so just like everything in this unit, have a ton of examples for partial fraction decomposition. Because you might have seen it before. I think I may have, looking back at my memories, I think I either learned it in high school or maybe early in college. But by the time I took my engineering math class, I forgot it. So we're definitely going to review it. Just so that you don't have it. Okay. But that's basically the 3-step process. So you take the Laplace transform of the entire differential equation, you algebraically solve for y of s. You may or may not have to do partial fraction decomposition, depending on the problem. And then once you've decomposed it, then you take the inverse Laplace to get for y. Okay. Any questions on this process here? Okay, all right, so we have about 5 minutes left, and so we obviously can't do too much in 5 minutes, but let me just start the review for partial fraction decomposition, and then we'll continue it on Tuesday. Okay. So the idea with partial fraction decomposition is that when you have situations where you have a complex kind of function in the denominator, we oftentimes want to break it up into kind of a simpler functions. And so instead of having one large fraction with a very complicated denominator, you would instead kind of break it up into, maybe 2 or 3 or 4 different terms, which much simpler denominators. Okay? And the reason we want to do this, or the reason we do this often in Laplace, is kind of motivated by by our method for taking inverse Laplace, right? And so when we take inverse Laplace, a lot of times what we're doing is we're just matching up a Laplace expression with the table. Okay, if you look at the table that we have in the in the notes, most of the denominators in that table are fairly simple. And so in order to use that table, basically in order to use the table method for computing inverse Laplace, oftentimes we're going to need to break up our denominators into kind of simpler expressions. So let's start. Yeah, let's start an example, and let's we will get through it. But at least you can kind of see the process. All right, so let's look at f of s equal to 3s plus 2 divided by s squared plus s. Okay. And so if we look at our denominator there, we have s squared plus s. And so there is nothing in the table that looks like that. Okay? We have s squared plus a constant, but not s squared plus s. Okay? And so as it is right now, we're not able to take the inverse of Laplace. Let's factor the denominator. I'm going to factor out an s from the denominator. Okay? And so we have s times s plus 1. Okay? And then up top, we have 3s plus 2. Okay. And so by factoring the denominator, we have this expression here. Okay? We don't know how to take the inverse Laplace of s squared plus s, but if we look at each component of the denominator, we have 1 over s, and we have 1 over s plus 1. Okay? Both of these individually are in the table. Okay? And so, what we can do, so if we're able to decompose this denominator into separate terms, one of them that's 1 over s, the other is 1 over s plus 1, then we would be able to solve for their expressions. And so the idea for partial fraction decomposition is this. And so if you look at your denominator and you have 2 expressions there that you want to break it up into, you can do it like this. And so what you have is your initial expression, 3s plus 2, okay, over s times s plus 1. And what you can do is you can break it up into 2 terms. So one term is going to be over s, which is the first part of the denominator. Okay. You're gonna break it up into another term, s plus one. Okay. So this one fraction is gonna become two, okay, where each of the two denominators is a component of the original. The tricky thing is that in order to make sure this is consistent, we need to solve for some unknown constants, big A and big B, okay, in order to make it work, okay, because we're decomposing this expression, but we don't want to mathematically change its value, okay? We're just kind of representing it in a different form that's more convenient. Okay. And so the whole idea of partial fraction decomposition is that we're going to kind of work on this expression, solve for A and B, and then decompose that denominator. Then we can take the Laplace of the individual terms. All right, any questions on this before we wrap it up for the week? Okay, all right, and so we'll stop here for today, and so we'll pick up this example here on Tuesday. If no one's told you yet, Monday is a holiday, so remind your Monday, Wednesday professors that they have no class on Monday if they don't say so. But for us, it doesn't affect us, so we'll have 2 lectures next week as. Okay. Hope you guys have a good long weekend. Hope you guys are able to rest a little bit. Thank you guys for coming today, and I will see you on Tuesday. That we want to get the basically we're going to get both the answers. You did 3 over s plus 1, and you introduce kind of an m here, s plus 1, and then your denominator wouldn't be. We want to kind of this form of the denominator here. We just want to change it.
We have Monday off, right? Oh, yeah.
Exactly. Yeah. So constant we can do it by but for the s term, you have to be a different. You don't want extra s terms. Like
The freaking the picture's too blurry.
Yeah.
Well, I mean, pull that shit up. I need to see what you put. When I saw you, when I thought of it, I was like, oh, come on, bro.
You want mistake when I got instead of
Yeah.
like I just like oh that's for the sake of something 0.6 and you for like writing.
Yeah, so for this one, I'm talking specifically about the form. So what you solved in part A was just
And it's sort of like 1.6.
and so that assumes a forcing term. When we have a forcing term, remember when we talk about resonance, if the forcing term frequency is the same as the natural frequency, that causes it to converge.
Like
Right, so this question is all about. Yeah.
But it was like the same. I mean, it's.
Ron, any final questions? Did you have something you wanted to ask?
Sure.
Okay, all right, so I'm gonna go close up the call, so hope you have a good weekend and we'll see you next week.